Welcome back to the show that tells you you are a quantum computer with free will, resonating with the fractal megastructure of reality to leave your body. My name is Justin Riddle, and this is episode 28 of the Quantum Consciousness series. In today's episode, we'll be discussing quantum teleportation, where the wave function of one qubit is transferred to and replaces the wave function of another qubit via entanglement. By the end of today's episode, we'll ask the question, could quantum teleportation be a mechanism for your mind to leave your brain when you die? This episode is available on YouTube, and an audio-only version is available on Spotify and Apple Podcast. If you like what you hear today, then please like this video, subscribe to this channel, leave a comment below, or for the audio listener, write a review.
Join me deep inside the mystery of numbers. Come and huff a metaphysical new. See how concepts become objects and then become qualia. Join us for an episode of Quantum Consciousness.
All right, so a little background on me as we get started here. I taught a course on quantum consciousness at UC Berkeley, and this series is really an update, extension, and further exploration of that material with a wider audience. So looking forward to hearing from you out there. In my day job, I'm a cognitive neuroscientist, and I deliver electric and magnetic brain stimulation in human participants to better understand the role of neural oscillations in cognition and to try to develop novel treatments for psychiatric illness. All right, so the layout for today's episode. First, I'm going to start off by giving a little bit of a motivation for why we would talk about quantum teleportation. And really this stems from these bizarre phenomenon of out-of-body experiences, near-death experiences, and reports of reincarnation. Next, I'm going to go into quantum entanglement and just give a little bit of backdrop on what quantum entanglement is and how this might be some sort of mechanism for understanding these bizarre phenomena. And then I'll go into quantum teleportation in specific and talk about how this could be used either in brain function or in starting to think about possible mechanisms for these bizarre phenomenon being somehow real. And then finally, I'm going to present an alternative explanation to quantum teleportation, which is somewhat related, but it relates to this idea of fractal resonance and fractal computation that I introduced in a previous episode. And it sort of gives unique predictions that are similar to the ones that we might find with quantum teleportation. All right, so to begin with, continuing from our previous episode where we talked about the idea of a quantum soul, today I'll be talking about some pretty bizarre experiences that some people have, namely out-of-body experiences, near-death experiences, and some reports of reincarnation. So to define what these are, out-of-body experiences are reported under a number of different drugs, some psychedelic drugs, for example, but also people experience, they have these out-of-body experiences typically during traumatic events. So people will have a car accident or some sort of, near-death experience. And it's a somewhat common report to have this experience of hovering above your body. You're looking down on this car accident and you're watching, the emergency medical personnel show up and they're working to resuscitate you. And then upon resuscitation, you snap back into your body and people will report these experiences, right? So they'll have these experiences. Another one is during heart attack. And so there's even people that have looked into cardiac wards where people are more likely to have a heart attack, and sort of querying and talking to people after they've experienced a heart attack and asking them, did you have any out-of-body experiences? What was it like? What did you see? What did you do? What did you hear? What did you experience, right? And so that has been widely reported, and so there's been sort of a growing interest in this phenomenon, right? And a more bizarre example is this idea of reincarnation, where, we don't really get to choose the reality we live in, but this happens to be the reality that we live in. And there's been a number of experiences of reincarnation or reports of particularly children having knowledge of a past life in some capacity. And, I think as a, typical science-focused individual, you might just completely be put off by this idea or this concept and just choose to reject any sort of thought or discussion of this being at all plausible. But there are certain individuals, like one person that stands out that did a lot of work in this field is Ian Stevenson at the University of Virginia. I'm not going to go through like all the details of the experiments that have been done, but he has gone and attempted to document a lot of these experiences that are being reported, particularly in other countries where reincarnation is a part of their belief system. Although it is reported in sort of Western societies where there isn't a belief system to support reincarnation typically, and yet it's still reported in those communities as well. So Ian Stevenson has gone around and tried to rigorously document this, and in some scenarios he has tried to experimentally verify by learning about a story of, let's say, a child, ask the child to say where his past life was at, and then to actually go travel to those locations and try to verify the details of their experiences without the kid actually going to that place themselves, right? So this is sort of a rigorous way where you could potentially find evidence for some experience like this. So you might be wondering out there, if this is reality, then where's the data? Where's the evidence for this experience? Why isn't this blasted on all the headlines? Reincarnation is real, you persist after you die. And I think this is a really good question. I used to think, if these paranormal anomalous experiences are actually real, then if there was ever just like a piece of evidence that we could run an experiment or figure something out, and we'd have undeniable facts showing that these have to be, it has to be real. And so, if we were just able to conduct that experiment or get that piece of data, this would like shake up the scientific community and there'd be headlines about this data. However, I would strongly question that scenario, right? Let's say we did find evidence of this, and Ian Stevenson and some of these other people would say that they have done these studies and they have found the evidence for this. Go look into it for yourself. But if there's no mechanism or no scientific understanding for how this could be possible, I don't think it matters if you were to show this reproducibly in a scientific setting. Even if everything worked out perfectly, you found definitive evidence of this reality, no one's going to believe it, period. No one's going to accept it. Even if you did it rigorously, there's always going to be someone saying, oh, well, there's got to be some other factors that explain this, blah, blah, blah. There has to be some confound hidden in the experiment to make it all, all BS, where it didn't actually work out the way you think it's working out, right? So I think what's really critical here is mechanism, right? And I think with the wave of quantum mechanics and quantum physics and starting to question this really physicalist, reductive worldview, we're starting to have new mechanisms and new ways of viewing ourselves that might give way to some of these phenomenon being plausible scientifically, right? And so I think rather than trying to prove any of these given phenomenon definitively, I think we need to just buy into the scientific paradigm and just take things one step at a time and sort of push the envelope to the next level. But people are trying to jump 30 levels into the future where we have definitive evidence of all these bizarre phenomenon. And I just don't think reality or the world, society is ready for those types of experiments to even be done. And I think, the next step is kind of just push the next frontier of science and then go from there. And once we have like a rigorous framework for technology and medicine involving quantum computers, for example, and phenomenon like entanglement are common practice, then we'll be at a point where we can then go look at these phenomenon. So that's kind of my personal conviction about this. So on that note, what in quantum mechanics has the essence or the feel of being able to explain something very bizarre like that? And what would this future science of out-of-body experiences look like? And so I think the best phenomenon is entanglement. And Albert Einstein called this spooky action at a distance. And so I'll describe, what is entanglement and why is it so bizarre and why does it have some of the components that might be relevant to these sort of like non-local phenomenon. And essentially, entanglement is a non-local, atemporal aspect of quantum physics where you can have two quantum bits or two systems, two photons, two electrons, just two parts, two systems of physical reality, and you get them entangled with each other. And once those two systems are now entangled, then when you separate them in space, then simultaneous measurement of both of those systems, so kind of looking at both systems simultaneously, they will have a correspondence with each other. So you can prepare these, let's use the example of pieces of light, photons. If you have two photons, you prepare them to be entangled and then you separate them. Simultaneous measurement of them, you'll find a correlation between your measurements. So there's different states that you can set them up in. They're called Bell states. And let's take one Bell state, for example, where they're either going to be 0, 0 or they're going to be 1, 1, right? So I measure the photons and it's going to tell me either a 0 or a 1. If I measure a 1 over here, I get a 1 over there. And if I measure a 0 over here, I get a 0 over there. So the two photon have correlated measurement results. And what's interesting here is that I'm measuring them simultaneously, and simultaneously to such a degree of temporal accuracy that there's no way that digital information or some sort of physical influence could travel between the two and cause them to be related, right? So in the physical universe, ignoring quantum mechanics, the speed of light is the fastest rate at which you could send information to each other. So if I want to get a 0 or a 1 from you, just some sort of like information, data of any kind, classical digital information, the maximum rate that you could transfer it is the speed of light. And that's because the speed of light is sort of the fastest thing in physical reality that we've been able to find. And there's certain reasons to believe that this is the maximum rate that you can send information. So back to the example of the entangled photons, if they are spread apart from each other and the distance is fairly great and you measure simultaneously, even if there was a photon that just happened to carry that information from one place to another, as unlikely as that is, you can measure them so simultaneously that even perfect information encoded into a photon traveling between the two, it wouldn't get there in time to influence that other photon that you're measuring, right? So this faster than light communication suggests to us that in the quantum realm, there's sort of this non-locality going on where the two photons actually are just one system. So even though they're separated in space, there's still one thing, right? There's still just one wave function or probability distribution, one system unifying these two photons, and it's as if they are just one thing, even though they're separated through great physical distances from each other. All right. So to put this in practical terms, a quantum computer is a way that we are able to sort of utilize these quantum properties, right? So in a digital computer, you have zeros and you have ones. In a quantum computer, you can have quantum information, which is essentially what is the probability of getting a 0 or a 1 when I measure that quantum bit. So this quantum bit can have sort of an arbitrary level of precision where you could have this probability for getting a 0, this probability for getting a 1, and it can have this sort of high degree of information being held in there. And that is the quantum information itself. However, when you measure it, all you can extract is digital information. So every time you look at that quantum bit or you try to extract something from it, you are basically locking it into one of the states that you are measuring that quantum bit. So there's a very simple way in a quantum computer to create a entanglement pair. So the way you do this is, let's say you have a quantum bit that is at state 0, right? So it's in state 0, and there's a 100% probability that it's in state 0 and a 0% probability that it's in state 1, right? And in a previous episode, I talked to you about how quantum bits actually have sort of two different dimensions to it, right? You have a 0-1 dimension and a plus-minus dimension, where the plus-minus dimension is like the momentum and the 0-1 dimension is like the position. And the more you know about one of them, the less you know about the other one. And I covered this in the uncertainty principle episode. So there's a quantum logic gate called the Hadamard gate. And when you pass the quantum bit through the Hadamard gate, then you're going to swap these two dimensions. So if I know that my quantum bit is in state 0, I prepare it in state 0, then that means the plus minus dimension is maximally smeared out. 50% probability plus, 50% probability minus. And when I pass it through the Hadamard gate, it's actually going to swap these dimensions. So now 0 and 1 are now 50% probability either option. And then the plus minus dimension is going to be locked into the plus state. But we're not really going to pay attention to the plus minus dimension during this quantum circuit. All right, so we passed the 0 qubit through the Hadamard gate. Now it has equal probability 0 and 1. And now the second gate that we're going to use is called a controlled NOT gate. The controlled NOT gate is fairly simple. It takes in two different quantum bits, and basically you're going to look at the first quantum bit, and then you're going to perform an action on the second quantum bit sometimes based on the result of that first quantum bit. So if it's a 0 coming into the top of this controlled NOT gate, then you don't do anything to the second quantum bit. So if a 0 comes in, then if it's a 0 or a 1 coming in at the bottom, it's just going to stay a 0 or a 1. However, if a 1 comes into the top gate, then it's going to flip the bit, that second quantum bit, right? So it's going to change it from 0 to 1 or from 1 to 0. So if the top one is a 0, do nothing to the second one. If the top one is a 1, then flip the bottom one. Okay, so now we're going to extend the circuit to have the Hadamard gate and the controlled NOT gate. And we're going to send in two zeros. 2 0 qubits are coming in. So the top qubit is going to go into the Hadamard gate. And now you have equal probability getting a 0 or a 1. And then the bottom 0 just passes right through. It's just on a wire. It keeps traveling. And now these two quantum bits are going to go into the controlled NOT gate, right? And what's interesting here is we now need to consider the superposition of 0 and 1 in that top quantum bit, right? So half of the time, a 0 comes in, and then the 0 at the bottom, nothing happens to it, so 2 zeros come out, right? But the other half of the time, there's a 1 coming into the top and a 0 coming into the bottom, so it's going to flip that 0 into a 1, right? So when you exit in that world, where the 1 is coming in. Now you have 2 1s exiting. So either you have a 50% probability of having 2 zeros coming out, or a 50% probability of 2 1s coming out, right? So our resulting system is either 0 and 0 or 1 and 1, right? And so what's really interesting here is that these 2 quantum bits are now entangled. And what this means is that you have to view the 2 quantum bits as a collective system, right? There's no way now to decompose the system into 2 separate systems. It's necessarily wrapped up into a single system, all right? And what's really interesting here is if I measure only one of the quantum bits, I instantaneously have information about the other one, right? So if I measure that, either one, pick one. I'll pick the top qubit. I measure that top qubit and I get a 0. That means the other qubit is in the 0 state. If I measure the top qubit and I get a 1, now I know that bottom qubit is in a 1 state, right? And what's cool is that when you apply that measurement, you're actually locking that other qubit into that state, right? So an action at one of the qubits is instantaneously changing the future of that other qubit. Now that wave function, which is spread out between the 2, measuring either of them irrevocably changes and alters that wave function of the 2 of them, right? And this happens instantaneously when either of them are measured. All right, so that is entanglement. Very technically, that is sort of how you create entangled pairs in a quantum computer. And so now we're going to dive into quantum teleportation and how this is a way of using entanglement to teleport wave functions around. Alrighty. So quantum teleportation. So in quantum teleportation, now we are going to harness the power of entanglement, right? So now the way that we typically think about this is you have one person named Alice and one person named Bob, person A, person B, right? And you're going to entangle a bunch of photons, but for the sake of this simple scenario, we'll just have one photon each, right? So each person has one qubit / photon, and we entangle them so that they are in this this setup like I just described previously, where it's either 0, 0 or 1, 1, right? So each of them has one of these qubits. Alice has a qubit, Bob has a qubit. We entangled them, and then we shot one of these photons over to Bob, right? So we had a little fiber optic cable, and Alice sent one of these qubits to Bob, and now he has like a repository of all these entangled qubits with Alice. So they have sort of a shared, I guess, like bucket of entangled qubits that are connected to each other. All right. So now Alice is going to send Bob a qubits wave function, right? So we have this qubit, and we're just going to say it's A probability 0, B probability 1. So it doesn't matter what it is. It's just some special wave function that has some meaningful quantum information. What those probabilities between 0 and 1 are is somehow meaningful, and it's unique. And there's this cool property in quantum mechanics called the no cloning theorem, right? So that A and that B, if it's a genuine quantum bit in the world, or you've have this history with this quantum bit, it's going to have a unique wave function associated with it that cannot be cloned or copied. So in a digital computer, all you have is zeros and ones, so you can copy it, right? Okay, you got 0, 1, 1, 0, 0, 1. Okay, I'll just make another string of 0, 0, 1, 1, 0, 1, whatever it was. But in quantum mechanics, you can create these unique wave functions that are not able to be cloned, right? Like the numbers describing those probabilities are so precise and so unique that there is no way to have another wave function that perfectly recreates that other wave function. So in quantum teleportation, we can transfer that wave function from Alice to Bob. Alrighty, so Alice has one of those entangled pairs, and then she has our special quantum bit that she's going to transfer. So we're going to have a circuit, and we're going to look at Alice's qubits. We'll put Alice's unique qubit at the top. In the middle row will be Alice's entangled pair, and in the bottom row will be Bob's entangled pair. So what you're going to do is you're going to entangle Alice's qubit, that special qubit, with the qubit that's one of the entangled pairs. How are we going to do this? We're going to use the controlled NOT gate, the same one we talked about previously. So her special qubit comes in, you pass it through the controlled NOT gate, and now that qubit is now entangled with her other qubit. And so what's bizarre here is now you've created a system where all three of these qubits are sharing this wave function together. And now that all of these three qubits are within a same wave function, they're now able to sort of shift around the data held within this system. And so what she does, and you can work through the math, and it's actually like pretty shockingly simple math here, because all you're doing is just this controlled NOT operation, and you can sort of work through the flow chart of all these different things. But what she does is she then passes that special qubit through a Hadamard gate, the same one that flips those bases, the plus minus and the 0-1 basis. So those get swapped, and now the resulting system is these three qubits. And now the final step for Alice is to measure both of her quantum bits, right? So she measures both of the quantum bits. It creates this chaotic collapse of the wave function. And now you either get 0, 0, 0, 1, 1, 0, or 1, 1. And essentially what this does is there is a superposition of Alice's two quantum bits and these different possible outcomes, and then Bob's quantum bit given each of these different outcomes. After measurement, now, depending on if you have 0, 0, 0, 1, 1, 0, or 1, 1, Bob's qubit is very similar to that original quantum bit that Alice was sending, except there's a couple things a little bit wonky with it, right? So chaotically, you can have a bit flip, you could have a phase flip where the sign of the 1 changes, or you could have a bit flip and a phase flip, right? And I talked about these in the error correction episode. So very similar to that error correction process from the previous episode, but essentially after Alice measures her two quantum bits, she can send Bob, hey Bob, that wave function that you got, it's pretty much the unique special wave function that I was sending to you, but the bits got flipped. So here, apply this bit flip function to your special quantum bit, and now it's the exact same one as I sent you. Or, oh, hey, Bob, you got a little phase flip over there in your special wave function I sent you. So now just apply this phase flip. Or, oh, hey, Bob, you got a bit flip and a phase flip. So just apply both of these to your wave function, and now it's good to go. Or, hey, it's good as is, and you can just use it. That is the special wave function that I sent you. Alrighty, so that is the algorithm. And there's a number of reasons why you'd want to do this in quantum mechanics. I won't go into all the reasons. Part of the reasons are mechanisms for making more robust coding. So you could imagine that special quantum bit is some quantum computation that you've been running. So let's say you're running all this like computation, there's some like futuristic quantum AI machine learning building up this really hyper unique special wave function. And now you have it and you're holding it and it's precious. And so now you want to transfer that unique special wave function around. And so this is a way where you could transfer that. Another application is cryptography. So you're trying to keep your passwords protected. And so imagine your password was this unique special wave function, but now you have to teleport it around whenever you want to use that wave function. You're at your bank and you need to put in your password. Well, let me teleport I set up a bunch of these special wave functions that are my passwords. I'm just going to use one of those right now. And so I'm going to teleport it to myself and then unlock my bank account, right? Futuristic password protection here. So a number of interesting practical ways that we could use this in our next level technology. And a lot of this, as I've covered in previous episodes, is being worked on. There's a lot of interesting revolutions occurring in the information technology space, and quantum teleportation is one of these foundational ways of manipulating quantum bits and sort of transferring information around. Okay, so yeah, there was a lot of technical stuff. So the question now is, what do I do with this knowledge, right? And so similar to our previous episodes, this is speculation. We don't know how, if at all, although I think there's strong evidence that biology is using quantum computation, we don't know how this would necessarily be implemented in biology. But hey, if we could do it in a lab, biology has been around for a very long time. And so is something like this occurring in the human body, right? And so to talk about quantum teleportation in the body, in the last episode, I talked about this idea of a conscious pilot, right? And so in the conscious pilot, there's some sort of like quantum computational entity. Maybe it's the equivalent of your mind, and it's moving around your brain and contributing meaningfully to ongoing quantum computations. So if I was a biological system and I was processing a bunch of quantum information, maybe I would want to create a bunch of entangled pairs and share them between different systems. And then in the future, when I'm running some quantum computation, I just take that resulting quantum computation, I entangle it to the existing, bank of entangled pairs, entangle it in there, measure those, and then suddenly that information shows up in that other system that I'm entangled to, right? So if you had a quantum computational system in biology, you would be looking for some mechanism of generating entangled pairs and then shuttling them into different parts of the body, and then in the future running some quantum computation, entangling it, and then measuring, and then that gets transferred over to that other part of the brain or of the body, right? And so, this is a wild concept and would require, a lot of infrastructure to get this going. However, I would like to point out just how fundamentally simple on some level this is. And it might be that quantum teleportation, in this laboratory setting where like we want the zeros and the ones to be very precise, in a more organic setting, there could just be some nuance to how the information is transferred. So what do I mean by this? All you have to do is entangle a couple pairs, send one somewhere else, and then you entangle this new information into that pair that you have, conduct a measurement, and then it shows up somewhere else. Maybe it's phase flipped, maybe it's bit flipped, maybe you don't care. Maybe there's some way where biology is just kind of shuttling information around and it's able to cope with or deal with the kind of imperfections that come through that measurement process. I don't know. Maybe there is a exact mechanism similar to the error correction episode's discussion where a protein is there and it conducts the measurement and it gets a 0 or a 1. And that is like when it does the measurement, the 0 is like, don't phosphorylate this part of the protein. And if it is a 1, then yeah, do phosphorylate that part of the protein. And then depending on if you got 0, 0, 1, 0, 0, 1, or 1, 1, the protein flips into some new conformation. And that conformation then applies a bit flip or something. So it could be implementing the bit flip, the phase flip, or the bit and phase flip, right? The problem with quantum teleportation, however, is that the beauty of quantum teleportation is this faster than light transfer of information, right? Faster than light transfer of quantum information. However, Alice is the one measuring. So even if there is a protein making these measurements, then the result of that measurement would have to be transferred over to Bob. And if Bob is another neuron or another protein system, on the other side of the cell or the other side of the brain, it's going to be a long time to get that information over there. And then, maybe the quantum information is that valuable that you do want to do that sort of transfer and then wait for the information to come in and then provide that update. But that does feel, I don't know, somehow a little bit too circuitous or burdensome to make that sort of precise quantum teleportation occur. Maybe there's some form of organic quantum teleportation that is messy and close enough, and you get some of the quantum information over there or the essence of the quantum information over there. And maybe there's some sort of like mass production of this transfer, right? So right now we're talking about the single qubit transfer from one place to another. But in the conscious pilot example, we're sort of imagining this large quantum computational force, this large wave function. If it's the self or some sort of like moving cognitive attentional system that's moving around the brain, there'd probably be a lot of quantum bits that you'd want to teleport from one place to another. So you're just like entangling all of this giant quantum information system, and then it's getting transferred to the other part of the brain or whatever. And I don't know, if you're undergoing all these bit and phase flips, does that totally like mangle the original quantum information that you intended to share? Or maybe part of it gets through and it's useful enough to have this kind of organic transfer. So yeah, those are the caveats. There's a lot to think about here. Maybe biology has been evolving for billions of years. Maybe there's some way that it's figured it out, right? There's some way where it's able to pull off quantum teleportation in some biologically meaningful way with mechanisms for enacting all these different things. All right. But we're here for the good stuff, right? The even deeper questions. So while it's a struggle to imagine quantum teleportation in a biological system, now we want to attempt to scale that up to encompass out-of-body experiences, near-death experiences, and potentially even something akin to reincarnation, right? What is the problem here? What are the challenges? So the idea is that your soul, yourself, your mind is some sort of wave function held within your brain, held within your body. That wave function could theoretically be teleported out of your body, right? There is, in principle, some way to teleport you if you were a wave function. Some nuances, some interesting things here. In the quantum teleportation mechanism, you have to perform this measurement on Alice's quantum bits. So in a way, you need to destroy the wave function that Alice is holding, and then it shows up with Bob, right? So could that be some sort of traumatic process, some sort of death process, where that measurement is the destruction of information locally, right? So instead of the measurement that Alice performs, plug in traumatic event, death occurring within the physical body, and that shunts the quantum information over to Bob. And here Bob would be some sort of repository of entangled qubits elsewhere, right? And it's kind of an open question. In a laboratory, once again, the entanglement state is very fragile, right? So it's very difficult to create and sustain entanglement between two different systems. And we live in this chaotic, noisy environment. So how could anything in a reliable way maintain entanglement through space and through time in any sort of dramatic way? Even in like the orchestrated objective reduction model, the microtubule model, the Stewart-Hameroff proposal, in those previous episodes, biology has to be working for billions of years to create sustainable systems for this. So how then would you have entangled quantum bits held elsewhere, still connected to your brain and your body, right? So I think this is the massive struggle to thinking about quantum teleportation meaningfully occurring between you and, after you have that traumatic car accident, there's quantum bits floating around in the ether around your body, and then you quantum teleport into this cloud of quantum bits hovering above you. That just does not seem feasible given what we know about like the destructive decoherent forces in reality. However, we're still learning about how quantum mechanics works, and yes, we have a great grasp on so many things about it, but there's still massive missing holes in the theory and are kind of, there might be more to this that could enable the essence of quantum teleportation, right? The fact that there's this non-clonable wave function that is you, there's some essence of how that could be shifted or moved around, right? And this is kind of this next question of what happens to quantum information. And so if your body is destroyed, what does that quantum information do? Does it just disappear? Does it just slip into the ether? And there was a paper by Deepak Chopra and Stuart Hameroff called The Quantum Soul, where they talk about out-of-body experiences, near-death experiences, and reincarnation. And they sort of ask this question, right? What happens to quantum information if, when you die, that information is still there, that wave function of you still exists in some form, and then it drops down into the resonance structure of reality, and it gets sort of like dispersed, or it clings together, and it's able to just sort of move around in this quantum universe that we live in. That quantum information somehow maintains its essence or its connectivity with itself, and then it can reemerge elsewhere or have some sort of conscious experience associated with it, because fundamentally all of reality is quantum mechanical and made out of the same elements. So there's like something that can still house that information as it goes into the lower levels of reality. And by lower levels, I mean like electrons and photons and atoms, right? Okay, but what does that really mean? And so I think the way they specify it is a little vague, and so I'm going to try to add my own flavor onto what this could be within the framework that I've been talking about in this series already. So I've been really pitching to you this idea of the three-world model, which is Roger Penrose is also a supporter of, but talking about this three-world model in terms of computation, where the physical world is digital computation, it's measurable, it's binarized. There's this mental cognitive realm, which is the quantum computational realm. And then there's this third world, this third level, which is sort of the Platonic world of mathematics, of meaning, of information in this sort of universal space, right? So a square, a perfect square, two parallel lines, this conceptual domain that is beyond any single individual and beyond the physical domain itself, because the physical domain is here and there, it's locally describable, and there's sort of the one true Platonic domain. But I equate that to potentially being some sort of fractal computation, some sort of resonance structure that goes across multiple scales. And this is a sort of radical new form of computation that we might come upon in the future. Very speculative. But thinking about this idea of quantum teleportation through the lens of fractal computation, okay? So the idea here is your mind is a quantum computer. You're in this physical body, but you're connected to this fractal resonance scale, this fractal resonance structure that goes from your brain into your cells, into your proteins, into your atoms, and maybe it even goes into higher orders beyond or bigger than your brain or bigger than your body. But let's just focus on maybe the micro scale because it's a little more biologically tractable, if you will. So you're a quantum computer, you're a quantum mind, and that quantum mind of yours is able to resonate down into these lower scales and then maybe emerge back up on some higher scales somewhere else, right? So the idea here is, could out-of-body experiences, near-death experiences, and maybe even reincarnation be a form of quantum teleportation, but you're teleporting within sort of this fractal entanglement structure where there's like this, I almost want to think of it as like an entanglement eddy. It's like this like spiraling current flowing of this wave function mind of yours, and it's embedded within this entanglement network, and it resonates down into some deeper levels and then can emerge back up, into other parts of the physical realm, or even back up into another, biological system itself, right? And so this is highly speculative and it's kind of just like a fun thing to think about. But let's think about it. So then quantum information within this sort of fractal domain, we're stretching for this new description here. So quantum information is this aspect of the quantum bit, this probability space, some state within this quantum probability space. But from an entanglement perspective, let's imagine this fractal resonance structure as having all these entanglement relationships to other parts of reality, right? Via the history of us on this planet, of biology, we're all sort of connected to this bigger, grander scale. And so you have all these entanglement relationships. And so you are sort of this eddy, this entanglement current, this like spiraling vortex of quantum information within this entanglement scale. And you are actively growing and building this reality that is you within the entanglement web. And so here, maybe it's quantum information in like the strict quantum computer sense. But like I talked about in the previous episode, the wave function collapse process is very intense and very destructive to quantum information. So potentially there needs to be some meta description or better understanding of quantum bits through time via this entanglement web. And so could there be a quantum soul or a consciousness that is you within this sort of entanglement web, within that fractal resonance? And I'm kind of like equating those two together, the entanglement web and this fractal resonance. And then that eddy, which is you, does survive death. And so when the host body, your body is destroyed when you die, that quantum information, that entanglement imprint is a very real thing, and it has to go somewhere. And so it moves around and it's looking for maybe a new quantum computer which is able to house the complexity of that quantum information eddy. But part of that, or whatever that is you, and it survives in some sense. So that is sort of where I'm going to leave you in terms of this model. Very speculative, fun to think about. Hopefully you learned something about how entanglement works, how quantum teleportation works. And I just want to emphasize, these are early days exploring a new technology, updating the digital computer view of ourselves to be a quantum computer view. And potentially there's more forms of information technology beyond the quantum computer, right? So how do we update? How do we radically accept the facts around us, the data around us? If there's empirical evidence for bizarre things that don't sit right with you, why don't they sit right with you? How can we explore this further and get a better sense of what it all means, And I think it is very sort of defeating and kind of like overly simple to just say, we disappear when we die. There's no point of anything. Nothing's meaningful. It's just chaos, and then it ends. But why is there something rather than nothing, right? Why are we here? Isn't it easier just to live in a void with nothingness? There's so much complexity around us, so much information. We have this conscious experience. There has to be more going on and a bigger purpose to our lives and to this reality. So the idea that we just disappear when we die, it's almost like too easy, and it's easy to defend because there's literally nothing to defend. You just say, "Hey, we disappear when we die," and it's like, "Oh, well, the burden is on you to prove to me that there's more than nothing," right? So it's easy for the skeptics to just push the burden of proof on the person who's stretching and thinking for ways that there could be more meaning to our lives. So just kind of want to end on this thought, I don't know what the answers are. I don't know if we survive death, maybe we can't ever know in our lifetimes. But question the people telling you that it's impossible. We're just coming into this new age, and there's so many new ideas that are going to emerge from this new technology, from this new science, from the future of science. And we really don't know the limitations to science and to technology, and we'll just have to wait and see. I think this is a really exciting time to be alive, and I look forward to talking more with you out there.